All right, we're gonna talk about potential well, and potential well is pretty much describing potential energy function. Okay, so if you were to graph potential energy function of a spring or block spring oscillating system, right? Then you will get a parabola like such. Okay, because potential energy of a spring is equal to 1 half kx squared. Now, x is the position, and u is the potential energy. So when you graph potential energy versus the position x, you'll get a quadratic graph, which is parabola or parabola, right? Now, this has to be understood completely. Okay, you have to really understand what's going on. Now, this u is equal to 1 half kx squared is the actual function itself, right? That's the equation. So when you graph it, you're going to get the plus side and the minus side of this position. If you were to look at this, where let's say there's a limit to this, okay? And the limit is if I stretch this thing like far enough out, a spring is going to break, right? Spring is going to break. Therefore, the maximum energy, there has to be a certain maximum energy level. I mean, you're not going to get an infinite potential energy out of this, right? So the E max is maximum energy it can possess by the system, all right? So at this level, the spring breaks off, right? And the block flies off, right? And uh, freed from spring, I guess, right? Then, if you were to actually, right? So like this thing, hopefully we're not going to be using this part, but we're just when we stretch it out to a certain point, right? We're just going to give the maximum uh, position change that we can do before it breaks off. So we're going to be staying within that in that the maximum like position where spring breaks. This maximum position that we're going to actually do is this is called amplitude, right? So at this point, the potential energy, right, is basically this is total mechanical energy that this system will possess. Okay, so at this point, when we stretch it out to position where A, which is the amplitude, is the maximum x position that system has, right? This happens to be the total mechanical energy. Or otherwise U max. Okay, so this is equal to U max. Okay, so at this position, this is your X max. Okay. Okay. So when I stretch the spring out to this position, that's the maximum stretch that I'm going to put into the system. That maximum stretch is known as the amplitude, A. Okay? So that's the total mechanical energy this thing will possess when I release this. So this, at this point, it would have the maximum potential energy. And as it goes back towards the equilibrium position, the potential energy will decrease, 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 and it gains kinetic energy. So at this location right here, at this location, right? It only has this much of potential energy, and the loss of that potential energy becomes the kinetic energy. Okay? So this is the kinetic energy, okay, at this point. I'm going to call that like, we'll call that X1. Okay? So the kinetic energy at 1 as well as potential energy at 1. Okay? So when I add these two energies up, it should equal to this maximum potential energy. Okay, I mean total mechanical energy. Okay, same thing. Okay, so at this point, this U1 is equal to, right, 1/2 kx1 squared. That's what this, right, this U1 is. Here, this would be this total mechanical energy minus this would represent my kinetic energy at 1. Does that make sense? Right? All right. Here, when it's at equilibrium, you would have V max. Here, at maximum amplitude or maximum X value, or at the amplitude, your V is equal to 0. Okay? All right. So for those of you who are familiar in chemistry, okay, this is very similar to Bohr's model of atom. Okay. So if you think about like ionization energy as the maximum energy the atom can possess, right? And then when it releases photon, I guess it drops to a next energy level, right? When it gains a photon, like the electron, goes up an energy level, right? Same thing, right? So if you think of this here as your ground state, right? And then your like energy level band 1 could be here somewhere, right? And then if you absorb an electron, then electron will actually, if you absorb a photon, then electron will gain an energy level, right? And then stay at the excited level, And then if it releases the photon, the electron will drop an energy level. It's the same thing. Okay? You could have all these different excited states depending on how much energy it jumps. Okay? You mean to put that down or? No, I'm not going to put that down. I'm just going to, I think, confuse some people. So just understand it this way, and I think it makes more sense for this chapter. Okay? The other side is going to be the same thing. The other side is going to be the same thing. Okay? So if you think about this being the total mechanical energy, and this total mechanical energy is equal to 1/2 k amplitude squared, anything that is less than that will be gained by the kinetic energy. And as it approaches to your equilibrium point, which is x naught, right, then your kinetic energy is maximum at this point, and your potential energy is zero. So if I were to draw a kinetic energy function for this, right, it'll be like that, right? So kinetic energy is the maximum, right, at equilibrium point, and minimum at the endpoints at amplitude, right? So it's like sort of like inverse of like that for kinetic energy function. Okay, so if you want, I guess you could put like one of these like dotted lines. Right, so this is like the kinetic energy, which is equal to 1/2 mv squared. So the maximum kinetic energy happens at equilibrium, right, at here. Minimum kinetic energy happens at the endpoints, because velocity is zero. All right. Yeah, that's all I'm gonna do to this page. Okay, I mean, I guess I could put more in there, like for all these other, ground state of energy and excited state energy level 1 and excited state energy level 2, but that's just gonna make more of a mess, I think. All right. Good. Next. So let's take a look at what this is then. So understanding potential energy function, right? Here, we know work done by a non-conservative force, right, is equal to, right, the negative change in potential energy, right? So this is actually a mathematical definition. So I'm going to actually put another equal sign on that thing. So this is actually mathematical definition. Okay? So this is mathematical definition of potential energy. Okay? This negative sign is very important. Okay? Now we already know that work done by a non-conservative force, or work done by a conservative force, is equal to the integral of, right, f of x dx, right, from x1 to x2. We learned that already, right? And it is a dot product of two vectors, so the result of it will be actually a scalar quantity. And we are also given that this is also negative, right, negative change in potential energy. So from here, we can set them equal to each other and say this now is equal to negative change in potential energy. Okay? So if given f of x, right, versus x graph, right, the area, right, under the graph of force versus x, right, is the negative change in potential energy. So basically, the area of the F versus X gives you the negative, right, change in potential energy, or we already know it as work done, right, or work done by conservative force. So once we know that, okay, you can always choose, right, to use zero potential energy at the reference point of your initial point. I mean, it just makes sense that way, right? This is like it's like always starting your stopwatch at zero because it's more convenient. Okay. In that case, you could say, right? So for this, if that's true, then your initial potential energy can go to zero. Okay. And that's important. That means we can say that this the integral of f of x dx is equal to negative potential energy function. Or remember the fundamental theorem of calculus? If you take a derivative of the integral, you get the function itself, right? If we take the derivative of both sides, then on this side, you're just going to get f of x, right? And if I move the dx, right, to the other side, here it's just a derivative, right? So if I were to look at this here, I only get f of x. Here, I get negative du of x dx. That means, right, force is basically the negative of the slope value of the potential energy function. And that's very important, that negative, right? So force is the negative slope value of the u of x. Or u of x versus x. Okay? So what does that mean? Well, let's take a look at, okay. I mean, if you were to look at this, let's give an example of this. So here, what is u of x? Okay. If, let's say, f of x is equal to 3x squared minus 2x plus 1. So this is just an example, okay? It's just an example. Then since u of x is equal to, I'm going to bring the negative to the other side. It's negative integral of, right, x1, which is x initial to x final, right? And let's let x initial equal to 0. And let x final is equal to x of 3x squared minus 2x plus 1 dx. So for those of you who are not familiar with integral in calculus yet, this is a good opportunity to learn how to use. So here, the negative of, when I integrate this, it'll be 3x cubed over 3, right, minus 2x squared over 2. It's like antiderivative, right, plus x to the 1 over 1, right? Evaluate it from 0 to x. So if I plug in the x, into the x, it's just going to stay as x, okay? And then if I plug in 0, it's going to be 0, 0, 0. So u of x then is equal to negative, right? This 3 over 3 will cancel out to 1, x cubed plus x squared minus x as my u of x. Okay? Now let's go backwards. What if u of x, right? What if u of x is equal to, let's say, negative 5x cubed plus 3. To find f of x, right, f of x is equal to negative du of x over dx. Right? That is negative d over, so I have to take a derivative of this function basically. So f of x then becomes negative, right, of negative 15x plus 0. This is like saying 3x to the 0 power, and then 0 times 3 is 0, and 0 times anything is just 0. Therefore, this becomes positive, right? Positive 15x as my f of x. Yeah? Oh, yeah, x squared. Thank you. X squared. I knew something was a little messed up. Thank you. All right, so this will be your force. This would be your force. Now, if you want to find out exactly how much newtons it is at certain position, you just plug in that value. So I want to know what's my force at like x equals 2. Then plug in 2 in for x, and then you'll know exactly how much force you have at that position. All right. All right. So here we go. So if I were to find, let's say, so here's my x, let's say, and here is my, let's say, u. Okay. And if I have a function, just use the same color here. If I, let's say, have function like this for my potential energy function, okay? So if I want to find the slope at this point, let's say, at, let's say here, x1. So the slope of this will be like that, right? So if once I find this slope value, the negative of this value will be my force. Okay, does that make sense? Okay, so this does that make sense? Okay, and the slope value here will be like 0, then your force will be 0. Right? I guess if you want to make it x2, right? And here, let's say if I want to like find the slope value at this point, right? And this will be like x3, and the slope, and since this slope here is positive slope, you're going to get a negative force, right? Okay. So this would be negative slope, so you're going to get a positive force. Here you're going to get a positive slope, so you're going to get a negative force. Right? All right, that's important. And here, if I were to look at it, if I had a f of x, and then this is x, right? Then, if I had, let's say, something like that, then if I were to, sorry, here's my x1, and here's my x2. Again, if you want to make this 0, then you just, right? The area underneath this, right, is basically my u of x, or change in u. Okay? And it should be negative. Okay. Now, if this were 0, then it'd be just, negative ux, but if it's not 0, then it'd be change in ux. Okay? So maybe I should write that down. Boom. All right. Any questions so far? All right, so how can we put this all together? Okay, well, let's take a look at some more complicated system, right, with all this different potential energy function with different like slopes and different curves and valleys. Okay, so look at this, right? So this is like the ground state right here, right? Excited state one and excited state two, and these energy levels, right? So if you think about this, okay, so this is basically the u of x function of x, okay? Um, think about the slope of this. Slope of this is 0, right? So the force is 0 when the slope is 0. Here, slope is 0. Force is also 0. Here, the slope is 0. Here, the slope is 0 instantaneously, right? So the forces all along here, at this instant, your force is going to be 0. Okay? So if you were to visualize this, think about it as though if you had a marble, okay, and you let the marble just basically roll on this u of x function as a track, okay. So um, let's write that down. So in general motion, right? General motion. Um, so example, object, right, released from rest, okay, at position x3, right? What happens? So x3, where's that? Oh, it's right here. At this location, we release the marble from rest, right? Let's pretend the marble rolls, right? Right? And think about what would happen. What would happen from here to here as it goes from x3 to x1? What should happen to that marble? Well, first of all, is it losing or is it gaining potential energy? What would you say? It's definitely losing potential energy. So what should happen to this marble if it's losing potential energy? It should be gaining kinetic energy, right? The amount of the potential energy loses, it should gain that much kinetic energy. That means it should definitely go faster, right? It should go faster. So from here to here, right? I guess I'm gonna draw it away from this line so that we can. Well, maybe I could draw this right on the line then. So here, this here is the, the kinetic energy that it gains, right? And this here is the potential energy that it still possesses. Okay? Maybe I should have drawn that in a different color. So the potential energy here. And kinetic energy here. So let's pretend that total energy at E3 right here is, I don't know, like 100 joules, like positive 100 joules. Okay, and then let's make this 0 joules. This is like the ground state. Okay, and we'll make this like 60 joules or something, and make this like 30 joules, or I don't know. We're just estimating. Okay. Okay. So at this point, when the marble's down here, right, it would have 30 joules of potential energy, right, and 70 joules of kinetic energy. Now, what about at this position? At this position, I have 0 potential energy, and it all converted into basically kinetic energy. Okay. At this point, like if you, let's say if it went down even further, then you would have negative potential energy down here. But it doesn't go down there anyway. All right. So this here would be 100 joules of kinetic energy, 0 joules of potential energy. Right here, we would have, right, 60 joules of potential energy and 40 joules of kinetic energy. Okay. So as it goes up, it's going to slow down, slow down, slow down, and then it goes over the hump. Will it go over the hump? Or will it just fall back down? Will it go over the hump? Why? Yeah, because this has enough kinetic energy to go over it, right? Because here you still have this much of kinetic energy, so it'll definitely go over, right? So it'll go over and then slows down and then speeds up, speeds up, speeds up, and then slows down, and then it's gonna actually go and then roll down the hair and so on. Okay. So if this were to go higher than 100 joules here, since we started here, it will only go up to 100 joules to here, and then you'll probably roll back down. It'll never go up any higher. Okay. All right. Now, at these locations, the critical points, okay, this here, when it's concave up, you have a stable situation. This right here at, at the peak, unstable. Unstable. Stable, stable, unstable. Here is very neutral. From, I mean, here, all when it's flat, when there's no force, it's very neutral. And so is this, neutral. Okay? Since slope is 0, right? Force is 0. Okay? So this will be the total mechanical energy of the system. okay? And this is basically potential energy plus the kinetic energy at any point, okay? And if you were to think about, the slope values, right? The slope value is 0. Therefore, your force is 0. Negative 0, or, right? Negative 0 or 0. So the slope value from here to here is 0. So the force value is negative 0 or 0. Okay? Similarly, right, the slope value from here to here right, the slope value here to here, right, is 0. Therefore, your force is 0. When your slope value is negative, your force is negative of negative, which is positive. At the inflection point, you're going to get the maximum force value. Okay, so okay, inflection point. So this inflection point right here, right? This is when it starts to, I mean, still negative slope, but negative slope value starts to change here to 0, towards 0, right? So at this point, your slope value is 0, right? And that's where this here 0 is, right? Slope is 0 here again. Slope is 0 here, right? So this is the slope, negative of the slope. Now here again, negative slope, positive force. Negative slope, positive force. Negative slope, positive force. But as it goes towards 0, it's 0 right here. Positive slope, negative force. Positive slope, negative force. Again, inflection point right here, right? Where you're going to get the maximum force value, right? Right here. Inflection point. So this, right? These are all 0 slope values. 0, 0, 0, right? And all these are 0. Cool? All right? So it's very important to understand that. Also, right, the area of this is the negative of the change in potential energy. Remember that? We talked about that, right? So this area here see, if I put negative there, it looks like it's part of the thing. So, right, area, right? So if you're going from force right, to um, potential energy, you have to integrate. Okay, so okay, so this is equal to negative area bounded, right? And then, right, these equilibrium points, right? These are equilibrium, 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 stable equilibrium, unstable equilibrium. Okay, so maybe we could write that down. Okay, maybe I should wrote that in green. Sorry. Okay, so there are three types of um, equilibrium. Okay, and basically one is neutral one, right? Two is stable, and three is unstable. All right, so we know what the neutrals are when it's like elongated zero slope are neutrals, right? Instantaneous tangent would be either stable or unstable. Stable is when you have a valley, right? When you have a valley like this. Unstable will be when you have a peak. Okay? This will not be an equilibrium. This is not an equilibrium. This is also not an equilibrium. Okay? So all this will be non equilibrium. Here, stable equilibrium, non equilibrium, unstable equilibrium, stable equilibrium, right? And then here will be just neutral because the slope, it's not going anywhere. It's just like standing. All right. All right. And if you go the other way, like this, I guess this is going from force to potential energy. But what if you're going from potential energy to force? You just take a derivative, right? So f of x is equal to negative of du of x dx. And that negative is very, very, very crucial. And that is basically negative slope value, right, of a tangent line, right? So, so if I were to take a slope of this tangent line at this point right here, right, or slope of tangent at this point, or slope of tangent at this point, and so on. That should give my negative force. Okay? Alrighty. So let's see if we can. Oh yeah, it's also important that it has to be given a starting point, right? For this particular thing to happen, must be given the UI, right? Where the starting point is. And that's important. All right. If we don't know where the starting point is, then it's just, I guess you could consider it zero, but it's not going to work out that way. All right. So let's see if we can actually do some, check our understanding and do this, and then maybe we can go over it. Okay. So let's see. I'll give you. I'll give you like 6 minutes, 7 minutes. So give it a shot. All right. I'll pause. I mean, the first one's really not that bad, right? Let's take a look. So from u of x to f of x, we need to find the slope, right? The negative slope, to be more precise, right? So f of x is equal to negative du of x dx. So find the negative slope, right, of tangents. Boom. All right. So I would just find slope values from all these critical points. So it looks like, I guess from 0 to 1 meters is here to here. So 0 minus negative 15 over, right, 1 minus 0. Right? So what is that? And you have to negative it. So you get positive, and then positive 15 over 1, and negative of that is negative 15. So this is negative 15. Here, looks like the same slope, right? It is 15 minus 0 over 2 minus 1, and you're going to have to negative it, and that is negative 15. So for first 2 meters, we'll make it negative 5, negative 10, negative 15, 0, 5, 10, 15, 20, 25, and so on, right? So first 2 meters, it looks like I have negative 15 newtons for the first 2 meters. Okay? So this is a little darker for everybody to see. Then, from 2 to 3 meters, it looks like 0. Right? So that's easy. So from 2 to 3, 0. This is good to make it a little bit. Right? So see it. And then, from 3, let's make it 3 to 5 because it looks like there's the same line, right? So for 3 to 5 is negative of, right? Negative 15 minus 15 over 5 minus 3, right? So what is that? That looks like negative 30, and the negative of that negative 30 is positive 30. So positive 30 divided by 2 is positive 15. So positive 15, okay, newtons. And then from 5 to 7, I guess, it's just 0, right? So 5 to 7 is just 0. Boom. That was it. Was that easy enough? Yeah, that was easy enough, right? Now let's go back. Now let's go the other way, okay? Now we're going to go from given f of x, we're going to go to the potential energy function. So this is like the negative integral of it, remember, right? So for this one, you have to do the negative integral. So u of x, or if you want, say delta u, is equal to negative integral of f of x dx. That means you have to find the negative area, right? Negative area. So if we were to look for the area of this is 8, right? 8 joules, I guess, if you want. So, but where do we start? Do we start just any random place? No, because this gives us the initial starting point. That means when x is 0, we have to start at positive 4 joules. Okay? So starting from positive 4 joules, we're going to go. Now this is 8, so we have to make it negative it. So negative 8 joules is what we have here for the first meter. So if we start at positive 4, we'll end up at negative 4, like so. Okay. And since it is looks like a constant, so you could do a straight line on this job. Okay. Then here will be 4, right? So it's negative 4, okay? And at 2 meters, we should have 0 slope. So if we go 4 more meters here, we should end up at 8, negative, and then it should sort of like flatten out as it approaches 2 meters, because the slope value at 2 should be 0. Okay? And then here again, this is negative 4, so this should be positive 4 joules here, right? From 2 to 3. So from negative 8, we go positive 4, so we should end up at negative 4 here. And it starts at 0 slope and then it sort of increases. Now, from 3 to 5, right, this whole thing is 8 times 2, which is negative 16, right, for the area. Therefore, since it's negative 16, it is positive 16 joules is what we have. So from here, negative 4, we're going to go all the way to 16 in the positive direction. So we're going to end up at 12 at 5 meters. Right? We should end up at 12. Let me see if this 12 is on the... Maybe I went up a little too high. 12 should be somewhere here, actually. And that should be 12 right there. And it should be a straight line because right, your slope value is constant value, so it should be straight line. And it's a negative, right? So it's positive slope. And then here will be negative 4. So that means this is positive 4 joules, right? Positive 4 joules. Therefore, from 5 to 6, we should end up at 16. So 16. And it goes towards 0. So it should flatten out at 6 meters, right? So it should be doing one of these joints. All right. So I guess maybe I should put a little bit of reference lines just so we could see that this should be 12 and this should be 16. All right, so hopefully that was good. Is that okay? All right, now we are finished. So I'm gonna go over homework problems Thursday when we meet. So please have your homework problems done and worked on it. You should be able to do every single one of them now. Okay. If you ever take a look at your Schoology, there's two packets for homework, right? One is just blank, and the other one is with hints. So if you ever get stuck doing your homework, like take a look at the one with hints. Okay, like if you, for example, like I give you hints. So if you take a look at it, if you get stuck, use the hints. Yeah, don't get used to it too much, but if you get really stuck, then take a look at it. You don't even have to print this out. You could just like open it up while you're working on your homework. All right. So please practice these. Also, I guess next week we'll do a little assessment on this. Now, chapter 9 is a monster chapter, and before we do start chapter 9, what we're going to do is we're going to actually do a little assessment, like AP type questions, like multiple choice questions, just to check your understanding. It's not going to count towards your grade. It's not going to really hurt your grade or help your grade, but it's going to just be a very nice self assessment to see how much you understand before we move on to chapter 9. Okay? It's not going to be a midterm. Okay, there's no such thing as midterm in this year, so don't be nervous about it. Right, all you have to do is just work on it and then just see if you understand it or not. It's just multiple choice. It's going to be on Schoology. Okay, and it should be one of those things that's going to help you say, oh wow, look at this, I really know a lot of things, or it's like, oh man, I better work on this. So that's all it is. So don't be nervous about it. It's not going to hurt your grade or help your grade. Doesn't mean you should just blow it off. you know it's a really good idea to really take it seriously and just to see where you are, especially for those of you who are taking the AP tests. I think it's a good idea to just give your self-assessment that way. All right, just so now we know we're done. So here we're going to end our lecture for today. Okay, and then I guess we'll stop.